Example 4, a person stands on the edge of a cliff that's 96 feet above the ground. He throws a ball vertically upward off the cliff with a velocity of 80 feet per second, and his height after t seconds is given by this equation. This is a projectile motion issue, and if you've been in physics, you've dealt with projectile motion. The gravity of Earth is negative 32 feet per second squared. That's exactly half of that times the quadratic term. 80 feet per second is the initial velocity upward, which is positive initial velocity times the linear variable t. And it's 96 feet above the ground, the initial position. So you can create a projectile motion equation on Earth or whatever planet you're on, actually, if you know the gravity of the planet. The initial velocity always goes in front of t. The initial position always goes as a constant. Half the gravity of the planet goes in front of t squared. And gravity is always negative because it's always pulling things down. If you have a planet with positive gravity, it'd be hard to walk. You'd be like thrown off the planet. You try and stand up and like, get away from me. You're shooting up in the air. It'd be kind of scary, I think. Anyway, so negative, gravity is always negative. It's always pulling things down. So it creates negative acceleration there. Okay, question A, maximum height reached by the ball. B, what's the velocity of the ball when it's 106 feet above and below or above the ground on the way up and down? When does the ball hit the ground? How fast is it traveling when it hits the ground? Okay, so again, they give us a position function. We're going to create a velocity function. Then we're going to answer the questions based on what we need to use. Okay, do I need the position function to answer this? Do I need the velocity function? Are they giving me t? Are they trying to find velocity? That kind of stuff. So depending on what they're asking you, you have to make sense of the question and what am I going to use for information to help answer this question. So what is the maximum height reached by the ball? Let's think that through. Maximum height has to do with position, right? Where it's at. All right? So I need to use the position function to answer the question. Okay, what do I need to know in order to answer the question? If I need to know what the position is, where it's at, so I need to find out what S equals, what do I need to know? What T equals. All right, at this point, do I know what T equals when the maximum height of the ball is attained? Okay, so now we have to start thinking about how can I find that out? Right? What do I know about this problem? What do I know about the physical attributes of Earth or planetary or projectile motion that tells me that there's a way to find out what T equals? All right, what happens when the ball reaches its maximum height?
It stops.
It stops. It stops as a speed, right? The velocity. So if we can find the velocity of 0 when the velocity of 0 happens, that means the ball stopped. All right, so that's question A. Anytime they ask for a maximum height on anything, the basic idea of that is, when does it stop? That's what you need to know. So if I take my velocity function, which is going to be the derivative of this, which is going to be 80 minus 32t, I set the velocity equal to 0 because that's when the ball stops. I'm going to get 80 is equal to 32t. Divide both sides by 32, we get t is equal to 2.5 seconds. Right? That's when it stops. So exactly 2.5 seconds after this person threw this ball upward with an initial speed of 80 feet per second, 2.5 seconds later the ball stops. Okay? So S of 2.5 is going to get me the maximum height of the ball. So it's going to be 96 plus 80 times 2.5 minus 16 times 2.5 squared. Whatever that comes out to. I would just type it in exactly like that. So 96 times 2.5 minus 16 times 2.5 squared equals, I typed it in wrong. 96 plus 80 times 2.5. There we go. I got 196. All right. Remember the ball started off at a height of 96 feet, right? So it actually traveled 100 more feet up. Okay, because again we have a cliff. Let me draw a little cliff here. There's our cliff. I'll make my cliff shorter. So this is 96 feet here. The ball goes another 100 feet. for a total height of 196 feet above the ground. Because here's the ground over here. That's where it's going to land.
So he throws it 100 feet higher than...
Yeah, basically. But again, the question is, what's the maximum height? The maximum height is from the ground. This is 96 feet above the ground. So the maximum height of the ball is 196 feet. All right? So that answers the question. I just wanted you, again, to get a feel for what's going on in the problem. We got some crazy person up here throwing a ball, trying to land on the ground. All right.
What if he has a partner down there catching it?
It could be a partner down there catching it. Maybe it's Odell Beckham Jr. That's
Maybe.
what, we can say that. And he's going to catch it one-handed with some kind of...
Or with his feet or something.
Yeah, maybe he'll catch it with his feet. That'd be even more impressive. All right. So, any concerns on that? Maximum height is a pretty typical question they ask in these problems, so make sure that you're comfortable with that. Velocity equals 0 is when the maximum height is occurring, and then S of that number gets you the actual height of the object. Okay. Part B, what's the velocity of the ball when it's 160 feet above the ground on its way up and on its way down? Okay. What is the velocity? Okay. We're asked to find velocity, so we need to use the v function, right? This is the v function. Okay. I'm trying to find v. What do I need to know to find v? T. Do I know t?
Yeah.
I know t for when it stops. Do I need no t for when it's 160 feet above the ground on the player?
No, sir.
No, we don't know that, do we? Right? But if I can find out when it's 160 feet above the ground, 160 feet above the ground is telling me S. Oops, that's a really bad drawing there. That's an arrow drawn to S. They're telling me S is 160. If I put 160 there, I can figure out t when 160 occurs, right? Make sense?
Yeah.
All right? Because we can see 160 happens, right? Because 196 is maximum, 160 is like here somewhere. So it has to go 160 on the way up, 160 on the way down. Those points have to be there. It's not going to be some like magical ball that disappears and reappears. So we're in the real world here. So for part B, I'm going to use the position function to find out what time it is when the ball is exactly where we want it to be. So I'm going to say 160 is equal to 96 plus 80t minus 16t squared. I like quadratics to be positive lead coefficients. I'm going to move everything to the left. So I'm going to get positive 16t squared minus 80t. And then 96 as a negative 96 adds to 160 makes positive 64. And again, I'm at a point here where I got an equation equal to 0. Everything's got a numerical, right? It's not v equals or s equals. So dividing everything by 16 is legal. T squared minus 5t plus 4 equals 0. And that one factors very easily to t minus 1, t minus 4. And I make my decision whether or not to use a quadratic formula based on the factoring. If I can see the factoring form immediately, I'm going to use factoring. If I can't, I'm going to use quadratic formula. That gets me t is equal to 1 second and 4 seconds. Now, can anybody give me a guess as to which one is the time on the way up and which one's the time on the way down? Can you give me a good reason why? Because there's an obvious answer to this, and there's a good reason why the obvious answer is what it is. But one of those is on the way up, one's on the way down. Which one do we think is which?
4 is on the way down, yeah.
All right, and why do you think that, Chris?
Because it's, yeah, longer time.
Yeah. And that's just the way that physically things work, right? It's going up to until 2.5 seconds, and it hits its maximum height. So going up has to be less than 2.5 seconds. 2.5 is when it stops, now it starts going back down, so 4 seconds. So the first time is going to be the up time, the second time is going to be the down time. Otherwise, again, you have reverse gravity. So you have a positive gravity planet where you try and stand on the planet, it tries to throw you off, and it's going to win because it's bigger than you. So we're going to deal with regular planets in this class. So usually the first time is going up, the second time is going down. So if I do v of 1 and v of 4, 1's going to give me the upward velocity, 4 is going to give me the downward velocity. If I substitute 1 into the velocity function, 80 minus 32 times 1, that's going to give me 48 meters per second, no, feet per second. So that 48 feet per second going up. If I do 80 minus 32 times 4, 32 times 4 is 128. 80 minus 128 is negative 48 feet per second. That is not a coincidence. Okay, if you're dealing with projectile motion, however fast something is at one point, it's going to have the opposite velocity going the other at the same point. So if it's positive 50, it'll be negative 50.
So it should have been, so it's an easy way to see if you're doing something wrong.
Yeah, exactly. If you get the positive or negative, and also that it's very, very easy to tell our assumption that 1 was the up, positive velocity, 4 was the down, negative velocity. The positive or negative tells us up and down also. The initial speed was 80 feet per second here, which means it's going to be 80 feet per second here, but negative. All right. If you shoot an arrow up in the air, don't do this.
A little roulette.
But if you shoot the arrow up in the air, however fast it's coming off your bow when you let go of it, it's going to be coming down the exact same speed when it comes down. So it'd be like, you know, just standing directly in front of the bow and it actually probably goes through your foot.
I've seen grown-ups.
Yeah, grown-ups where that happens, yeah. That's not a good game to play. Don't ever do that. But again, especially arrows too, because they're aerodynamic, so friction's going to slow things down, but with good aerodynamics, the exact same speed you let it go is the speed it's going to be coming down when it hits, so be careful of that kind of stuff. All right, question C. When does the ball hit the ground? The ground being here. All right, so when does the ball hit the ground? So what they're asking for with when is time. Okay, what's true as the ball hits the ground? Do we know anything specifically about position or velocity? Okay, S equals 0. The stopping thing, what Chris said is typical. Students think about that. As it hits the ground, the speed is going to be 0. But as it hits the ground, the speed is going to be however fast it's going. Okay, we're looking at the moment it touches the ground. It's going super fast. All right. It'll stop eventually after it bounces a few times. It's a ball, so it'll bounce sometimes. But eventually it stops and it's sitting on the ground at a velocity of 0. But as it's making contact with the ground, its velocity is actually rather fast. Faster than 80 feet per second, to be honest. So when does it hit the ground is S equals 0. That's going to be the fact. Anytime you want to know about it hitting the ground, it has to have a height of 0 then. So to do part C, the position function, which is this 96 plus 80t minus 16t squared, I want that to equal 0. Again, I got a quadratic equation equal to 0. I like my quadratic term to be positive, so I'm going to move everything left. So 16t squared minus 80t minus 96 is equal to 0. Everything divides by 16 again, so I'm going to get t squared minus 5t minus 6 equals 0. Again, looking at factoring, if I can see an easy way to factor it, t minus 6 times t plus 1. That gets me a time of 6 seconds or negative 1 second. Which of those two numbers do you think we want?
6.
We want 6, right? Because negative 1 happened before we let go of the ball. All right, so at the moment we let go of the ball, that's time equals 0. Any time before 0 doesn't count. So 6 seconds. So question C, when does it hit the ground? At 6 seconds. Question D, how fast is it traveling when it hits the ground? How fast is a question of velocity, right? And if I need to know the velocity, what do I need to know? Time. Do I know the time? Absolutely. We just figured out that it hits the ground at 6 seconds, so we can figure out the exact velocity at 6 seconds. So if we do, for part D, we just don't want to do v of 6. That's going to be 80 minus 32t. That's going to be 80 minus 192. So negative 112 feet per second is going to be the speed of the ball. The initial speed of the ball was 54 miles an hour. When it hits the ground, it's 76 miles an hour. Again, we're dealing with a perfect world with no friction, so it doesn't slow down because of that. But still, it's going faster when that happens.